Welcome to 3.4, Acid-Base Titrations. If you need to look at your textbook to help with this, it's on page 39 to 41. So lesson objectives for today are to understand the typical shape of pH curves for acid-base titrations in all combinations of weak and strong monoprotic acids and bases, and be able to perform calculations for titrations of monoprotic and diprotic acids with sodium hydroxide based on experimental results. So at GCSE you will have met titrations already, and at AS level we did them as well. So a titration is where we find out the concentration of an unknown solution by reacting it with a solution of known concentration. And when we do this, we normally add an indicator so that we can see when the solutions have been neutralized. There are a few examples of reactions which are self-indicating where we don't need to do this, but for most of them we have to add an indicator, and we'll talk in 3.5 about how we choose these indicators. So what if we were to use a pH probe instead of an indicator? What would happen? So if we were to do this, we would have to calibrate the pH probe by putting in a buffer solution. And don't worry at the moment about what buffer solution is, because we'll talk about that in 3.6. Now, if we did this experiment, so instead of having an indicator, we measured the pH after every addition, then we would see a graph of the pH against the volume added. And we would see this as a curve. And the curve we see is going to be different depending on whether we've got strong and weak acids and bases. So here we have two graphs which show the on the left hand side we're adding strong acid, and on the right hand side we're adding strong base. So if you look at figure 1 where we're adding strong acid, there's two lines on there. There's the first one where you're adding strong acid to a strong base, so you're starting off with a strong base, so of course it's starting off with a high pH, so it's starting off there at 13, pH 13. So it starts off at pH 13, and as we add strong acid, it very gradually goes down until we get that sharp line. So we get a sharp vertical line, and where that sharp vertical line is, we call the equivalence point or the end point, and that's where it's been neutralized. And then you can see once you get past that neutralization point, if you keep adding more acid, eventually the pH gradually decreases and you end up with a pH there of about 2. So because it's a strong base, you're starting off with pH 13. Because it's a strong acid, you're ending up with a pH of about 2 on that case. Now when we have a weak base, then it's going to be slightly different. So again we're looking at the left hand diagram, but we're adding strong acid to a weak base. So because it's a weaker base, it starts off at a lower pH. So that one's starting off at about pH 11. So its pH is lower, obviously, because it's a weaker base rather than the strong base which had pH 13. So it starts off lower. Again you get this gradual decrease as you add some strong acid, and again you get that sharp vertical line where you've got neutralization. But as you can see from that left hand graph, the vertical section is much smaller in height than it was for the strong base and the strong acid. So because we've started with a weak base, we've got an endpoint that's less sharp. But then at the end, when you're adding the strong acid again after the neutralization, you're getting exactly the same curve. Now on the right hand side, you've got the different example. In this case we're adding strong base. So we can either start off with a weak acid or a strong acid. So the bottom line represents a strong acid, and we're starting off there with a pH of 1, so it's a very strong acid. And as we add the strong base, again it gradually goes up, and then you get that really sharp vertical line to show the equivalence point or the end point. And then once you've got past that end point, it then gradually increases again to give you a pH there of about 12. So that's when you start adding strong base to strong acid. Now the weak acid, you can see you're only starting off at about 11, sorry I'm going the wrong way. You're starting off at about pH 3, so it's a weaker acid. And again, as you add the strong base, it neutralizes, it goes gradually, and then you get that end point, and then you get a gradual increase again. So again, as with the left hand diagram, for the weak acid compared to the strong acid, you've got a smaller height for that curve, for the vertical line. And that means you've got a less defined endpoint. Okay. Now, if the acid was added to the base, then the pH curves would look a similar shape, but they'd be flipped around the pH 7 line. So the last example that we need to look at is if we add a weak acid to a weak base, or a weak base to a weak acid. And as you can see here, there's no real strong equivalence point. So you haven't got that vertical line in the middle section that we had on the other graphs that we were looking at. And this is why we can't titrate a weak base against a weak acid, because you haven't got that strong endpoint, so you haven't got a sharp change in pH where we can measure. So just to reiterate, the endpoint's the vertical section of the line, the endpoint's unclear in the weak acid, weak base titrations, and the endpoint is where neutralization has occurred, so that means that all of the H plus and the OH minus have reacted together. Now this confuses some people, but it's not always pH 7. Okay, if you've got a strong acid and a strong base, it's going to be pH 7. But if you're going to have a weak base or a weak acid with a strong base or a strong acid, then it's not going to be pH 7 when it's neutralized. But all that H plus and OH minus will have reacted together. So what we need to look at now is some calculations from titrations. And you need to approach this stepwise, as you do with all calculations, in order to make sure that you don't make a mistake. So the first thing you need to do is write the balanced equations. Then you need to calculate the number of moles in a known solution, and you should be familiar with this equation from AS level chemistry. So the number of moles is equal to M, which is the concentration, times by the volume, divided by 1,000. And in this case, V is the volume in centimeters cubed. So once you've done that, you then need to calculate the number of moles of the unknown using the balanced equation, and then calculate the concentration of the unknown solution using concentration equals 1,000 times N divided by V. And that equation that we're using in 4 is just a rearranged equation that we're using in step 2. So we've talked about what the 4 steps are. Here's an example of a calculation that you could do using those stepwise instructions. So in bold we have the question that you'll be given, which is 25 centimeters cubed of 0.2 mole per decimeter cubed. Potassium hydroxide neutralizes 10 centimeters cubed of hydrochloric acid. What is the concentration of the acid? So first thing you need to do is write the balanced equation, which is written here. So you've got KOH plus HCl gives KCl plus H2O. So that's our balanced equation. So now we can move to step 2. So step 2, if you remember, was to calculate the number of moles in the known solution using the equation shown. So you're just simply substituting your numbers in, because in the question it tells us the concentration of the known solution. So the known concentration solution here is your potassium hydroxide. So we know from the question that it's 0.2 moles per decimeter cubed, and we know that we've used 25 centimeters cubed. So the expression for the number of moles becomes 0.2 times 25 divided by 1,000. And if you put that into your calculator, then it's 0.005. So that's how many moles of potassium hydroxide we've got. Now in this case, if you look at the balanced equation, then 1 mole of KOH reacts with 1 mole of hydrochloric acid. So the number of moles of potassium hydroxide is going to be exactly the same as the number of moles of HCl. So we just worked out that we've got 0.005 moles of KOH, so that's also how much hydrochloric acid we've got. So now we can go to step 4 to calculate the concentration of the unknown solution, and that becomes 1,000 times N divided by V. We've just worked out that N is 0.005, so we're timesing that by 1,000, and then divided by 10, because in the question it says the potassium hydroxide neutralizes 10 centimeters cubed of hydrochloric acid. So that's that 10 centimeters cubed that we need to put in that expression. And if we put that into our calculator, we get 0.5 molar. The common mistakes in exam questions like this is to not remember the equations correctly. So you must make sure that you learn them and that you can either rearrange them or you remember them in all different forms. And the second mistake that people commonly make is to get the volumes mixed up. So to use 10 centimeters cubed for the potassium hydroxide or 25 for the hydrochloric acid. So make sure you're reading the question carefully and transferring the information into your correct place in your calculation. Now just a quick aside before we finish is that if the acid was diprotic, so for example H2SO4 would give you 2 H pluses, then you have to remember that the concentration of H plus is going to be twice the concentration of the acid. So if you've got a diprotic acid, then you've got two problems, probably. The first one being that your balanced equation, you may have a ratio of 2 moles of your alkali to 1 mole of your acid, because your acid will contribute 2 H pluses. So for example, H2SO4 would react with 2 KOHs, because you've got 2 hydroxides there to match the 2 H pluses. So when you work out your number of moles in step 3, you'd have to remember that there would be twice as many moles of the KOH as there would be for the H2SO4. So your number of moles of H2SO4 would be half what you've got of your KOH. So you've got to remember that, and you've also got to remember that the concentration of the H plus is going to be twice the concentration of the acid. So here's our lesson objectives, which were to understand the typical shape of pH curves for acid-base titrations in all combinations of weak and strong monoprotic acids and bases, and to be able to perform calculations for titrations of monoprotic and diprotic acids with sodium hydroxide based on experimental results. Now, as usual, if you don't understand either of these lesson objectives, then go back over your notes, watch the video, look at textbook, look online, find some way to address this before you come to lesson.